When we first introduced the hapkit board, we showed you how to turn an LED on by using one of the digital output signals. So basically, the LED was on or off. Now we're going to talk in more detail about how to do analog inputs and outputs, which is really important for being able to both read from sensors for your hapkit as well as output commands to the motor. So it's important to understand the difference between digital and analog signals. In mechatronic systems like the hapkit, where you are dealing with both electrical systems and mechanical systems, you really need to understand both analog or continuous as well as digital or discrete signals, because both types are used to transmit information. So an important thing about analog information is that it continuously varies in amplitude. So it might go up or it might go down, and there might be a bunch of different possible values of the voltage. And depending on the resolution of whatever kind of board you're using, in this case your hapkit board, there's a different level with which analog information can be either interpreted or sent out. And we'll talk more about that resolution in a little bit. But the idea is that for an analog signal, a truly analog signal, you have voltages which are going to be changing in time. And those might have to be read or output by a mechatronic board. On the other hand, you have digital information, which is either going to be high or low. And typically for boards like the hapkit board and the Arduino, a low voltage will be anything that's under about 0.2 volts or so, and anything that's considered high will be above around 1.8 or 2 volts. But ideally is you would say that low is 0 volts and high is 5 volts. And that voltage might be high or low at any time, but the idea is that it is not really anywhere in between. Now, from the point of view of the code that's in your hapkit, the Arduino code that you write, something that's high is considered a 1, or if it's low, it's considered a 0. And so this is binary. That is, there's either two possible values for the signal. It's high or low. And the fact that it happens to be 0 volts or 5 volts doesn't really matter. It's just important that it be high or low. So let's talk a little about binary counting, because you're going to encounter numbers like this quite a bit in programming these sorts of systems, and it's important that you get used to this idea that because digital systems compute in terms of ones and zeros, you have to understand this base 2 counting system. So we're going to build up a table over here in which we're going to give some various binary numbers and their decimal equivalents. Now, when you actually program things into your hapkit or any Arduino-based board, you'll really usually be using the decimal number. But it's important to understand how this relates to binary. So let's walk through some examples of binary and decimal combinations. So the first one's probably pretty obvious. We're looking at a binary situation where we have 4 bits. That is, there's 4 possible locations that can either be ones or zeros. And I guess it's important now to mention that the number on the left is going to be the MSB, or most significant bit. And the one on the right side is going to be the least significant bit, LSB, which stands for least significant bit. Okay, and so binary 000 is just going to be decimal 0. It doesn't really matter actually how many bits you're considering. A bunch of zeros is just a 0 in decimal, which is our typical base 10 counting system. So let's start counting up now. So let's take the least significant bit on the binary numbers and make it into a 1. Well, that's equivalent to a decimal 1. But things get more interesting when you go on to the next step. So in binary, if you want to go on to the next number, well, each one of these slots can only be a 0 or a 1. And so your next one over, your second bit, has to change to a 1, and your least significant bit goes back to a 0. And in decimal, that signifies the number 2. And so we can keep counting up in that way. A 0011 is a 3, a 100 is a 4, and etc. You go 5, I skipped a few numbers to get all the way to 8. Now, if you have a 4-bit system, that is, it can keep track of ones and zeros in 4 slots, you might want to think about what is the largest decimal number that could be recorded. And in this case, let's say we kept counting upwards, we could get all the way to 1111, and that would actually be 15. And it's important to note that although we get up to the decimal number 15, there's actually 16 values which can be recorded in this case. So given 4 bits, you have 16 possible decimal values ranging from 0 to 15 that could be selected. Now, one sort of fun thing to do is actually to learn how to count in binary on your hand, and that actually can be useful for just doing some quick calculations. So since I'll give you a quiz question about this later, I'm just going to sketch a little bit about how that would work. So let's say here's your hand. We have 4 fingers and a thumb. And so if you wanted to do 0, you would put your hand in a fist. So you'd have no fingers up. And if you wanted to do a 1, you would just put 1 finger up. And if you wanted to do a 2, you would put the first 3 fingers down, the 4th finger up, and then the 3rd finger down. And if you wanted to do a 3, you would keep going, and now you would have 2 fingers up. And you can see how this 3 here corresponds to this shape here. There's a 0, 0, 1, 1. Sorry, actually, I drew a 5-fingered hand, which means we're actually talking about 5 bits, not 4. But anyways, the idea is here there's an extra 0, which could make it a higher number of bits. But in any case, zeros followed by a 1, 1 result in a 3 decimal number. So good practice for learning binary, and something I encourage you to do if you just haven't played with binary numbers before and want to get a good feel for them. Okay, so some important ideas about binary counting and being able to know how much information can be stored in a computer system that stores things in bits. So I mentioned already, you need to know what is the most significant bit and what is the least significant bit. And that is, the most significant bit is the left-hand side. That's the most significant bit. And the least significant bit is on the right-hand side of the list. The second point is that n bits can represent 2 to the power of n decimal numbers. And you can see this example just from this problem here. So here we had 4 bits, that is 4 bits of information, and so we should be able to get 2 to the 4th decimal numbers. And so that's 2 times 2 times 2 times 2, which should equal 16 because we have 16 different decimal numbers that could be represented. So if later on you hear, oh, I have a, say, 16-bit board, you know that it can store information up to a resolution of 2 to the 16, parts. So that's the number of decimal numbers that can be represented by a certain number of bits. So I'll also point out that a common unit that you may have heard of in just computing in general is the idea of a byte. So people might say, I have a 10 megabyte file, I have a 100 gigabyte hard drive, etc. And 8 bits is a byte. So this is 4 bits, so that's not a full byte, it's a half a byte. But the point is that this is a very common unit. So if you want to start getting an intuition for how much information can be stored on any digital system, remember that 8 of these bits, these zeros and ones changing between each other, is a byte.